Good afternoon. And this has been an enjoyable pursuit. I started attending the Augmented World Expo about 5 years ago. At that time, we were exploring the use cases, exploring the types of solutions. We heard from enterprise colleagues, the use cases, the challenges, the lessons learned, and it's been quite the pursuit since then. We're excited to show you today what that has resulted in. One of the questions that I get from our executives when we're working through augmented reality use cases is, what are your numbers? Show me the numbers. And that's also what we hear from the enterprise. Enterprise wants to see what our numbers look like. So today I'm very pleased to be able to show you some of our numbers. We won't have enough time to talk about the full ROI, but we will show you some elements that feed into our ROI. And we've had a lot of fun with these numbers, I have to say. Today with me, I have Jory, who builds spacecraft, human spaceflight spacecraft. I also have Chatman, who's our lead augmented reality shop aid developer for this pursuit. And then I'd also like to say a thank you to the technology partners who are with us today. We've seen how the technology has changed over the last decade, how you have an idea and you follow that idea and you pursue that idea and you turn it into something real that benefits companies like Lockheed. We're very grateful for that. We knew that we would be able to use this type of technology in the early, say, 2020s in our manufacturing environments, but we've accelerated that, and now we're able to see solutions on the manufacturing floor, building spacecraft. So someday really is closer than what we thought it would have been. Our business areas, Lockheed Martin is made up of 4 business areas. It's space systems, aeronautics, rotary mission systems, and missiles and fire control. Today we'll talk through the space systems use cases for the manufacturing environment. When you look at the numbers, we're building very large numbers in terms of satellites and spacecraft. 800 satellites in the last 50 years. But that's a very small number in terms of manufacturing. Manufacturing environments are building tens of thousands or hundreds of thousands or even more. And so, relatively speaking, we're in a very small number range. There's a perception that the way that you save money is by saving money per unit. And then when you multiply that by 10,000 or the hundreds of thousands, you save a lot of money. And that it's not really worth the pursuit when you're building small numbers, and we've proven that to be incorrect. We've shown that we can save significant money, time, reduce errors through this process. We're also applying this technology. It's a very high value hardware where quality is absolutely critical. Of course, you don't have a great opportunity to modify or to maintain a spacecraft once it's launched. So it has to be absolutely as close to perfect as possible before it is launched. Tolerance is also the tolerances that we're working to. Decker, what's the 4 to 5 digit decimal tolerance? So that kind of gives you an idea. You split a hair 4 times, and that's the tolerance level that we're looking at. So having good information that's reliable in a timely manner is significant within our environments. Before we talk through the use cases, I wanted to talk about how we measure. Because when we're applying the technology, when we're selecting use cases, it's very important that we pick use cases where the solution is providing a return. The way that we go about this is we use the Ooda Loop, which is, the Ooda was designed by an Air Force Colonel, John Boyd. It's broken up into 4 categories: observe, orient, decide, and act. When we look at the manufacturing environment, we can divide up the activity into these categories, and that helps us to go in and start running metrics and quantifying where we are saving, where we can save, where there's rich opportunity to save. And here's an example. When we broke this down, observing is looking at the paper instructions or the digital instructions. Orienting is taking that data and mapping it onto the physical components and understanding how that drawing relates to the physical component. The decision process usually involves quality or DCMA, additional people to verify the steps that are about to be performed are the correct steps to take. And then the action is actually drilling or applying torque. What we found was that with these small number builds, about 50% of the time is spent in that observe, orient, decide block. That's a significant amount of time. That's half the time is being spent finding the information, verifying that the information is correct, and checking it with our peers to make sure that it's absolutely correct before we take the next step for the action. This leaves a fantastic opportunity to optimize. If we can take out even a significant, a third of that time, that would be a huge reduction for us. So Decker is going to talk through a use case, one of the specific use cases that we apply this to with torque applications, where we applied this observe, orient, decide, act approach.
So before we get into the numbers that we got from the results, I wanted to give you guys a little bit of briefing on the hardware that we're using. So we did this activity on NASA's Orion forward bay cover. The forward bay cover is the top third of the capsule. The main purpose of the forward bay cover is to protect the series of parachutes during reentry, and then it will get jettisoned again to let the parachutes slow the vehicle down for a water landing. During reentry, the vehicle will see speeds near 25,000 miles per hour, and it will endure heat of around 4,000 degrees Fahrenheit. When the forward bay cover is separated from the capsule, it will see an equivalent of 26,000 pounds of force. So building a quality product is our main goal. Torquing the panels is done 6 times. There's 6 panels that we torque to the wells and the deck, and the information, finding the information to do the torquing action is found from 3 different sources. So we get information from the manufacturing work instruction, we get information from the engineering drawing, and we get information from our internal site where we keep specs zip coded from the engineering drawing. So all of that information for torquing comes from those places, and that takes up about 15% of the overall activity. At this point, a technician usually creates some kind of shop aid or template to put the information that they just gathered on the flight hardware itself. You can see in this picture, they used tape and they wrote down a torque sequence, they wrote down proper running torque, what the final torque would be, and that usually takes, as we showed here, 8% of the total activity time. At this point, the technician usually gets a quality engineer to verify that the information is correct and to verify that the placement of the information is correct before doing the activity of torquing. This is like a measure twice, cut once scenario, and that ends up taking 28% of the overall time. So collectively, Amanda, Shelley, and I thought that this was a place where utilizing augmented reality could drastically change those times. You can see the observe, orient, and decide takes up 50% of the whole action of torquing. Throughout this process, we created a digital first-person work instruction, and we utilized augmented reality and anchoring holograms in space on the assembly that shows the same information that you see the technicians taping here. Originally, we thought we could maybe decrease the information overhead times by 35%. We thought that would be a pretty aggressive number, but after doing this activity, the numbers were shocking. Shelley is going to show on this slide the information overhead was reduced by 99%. So really what we're talking about here is a race for information. The traditional method is a slow and arduous task that can be the crux of my job. But by utilizing this technology, we have a much faster racehorse to get to that information. Now, you see in this slide, this is what our overlay looks like. You'll see all of those fasteners have numbers on them. That's the torque sequence. You'll see they're color coordinated to a specific torque value and final torque value. In this picture, you'll see that there's 5 different colors, so all of those get torqued to a different value. And this really is just the tip of the iceberg. We created a work instruction from the very beginning of this build to the very end, and we can make this assembly per print without a manufacturing work instruction and without an engineering drawing, just solely by utilizing augmented reality and holograms. So we'll dive into some more of these numbers. I'm going to pass it over to Amanda, who's going to follow up with some more of our results.
So as Shelley said earlier, our primary objectives were reducing the time spent in just gathering information. So the most staggering number we found was that 85% reduction in time you see on the far left. That was time spent ramping up a technician. So previously, this would take about 8 hours for a technician to look through the drawings, the MWI, the manufacturing work instruction, and become familiar with it. Now we're looking at 45 minutes for the exact same task. Moving over, we see the alignment. That's a tooling placement and alignment on the hardware, and DFI is another type of drilling activity. These numbers are actually a little bit conservative. At the time, we were including the time spent to boot up the device into our values. So we were doing things a little bit differently back then. We used to start up the device whenever we needed it and just glance at it several times throughout the day. Now we're starting it up at the beginning of the day and leaving it powered on. And that's how we're getting into the 90th percentile. You'll notice 2 identical drilling categories. The one on the left is actually Decker's team working on this. So it's technicians that have done this build several times over. The one on the right is technicians that are experienced, but not with this particular build. And we were amazed to see a 3% difference in that time. So it's showing us that you can take technicians that aren't familiar with this hardware and pass along that tribal knowledge and that experience and reduce ramp-up time and get them going just as fast as a seasoned technician. And then the farthest column over is the torque patterns that Decker had already talked to. This shows the overall activity time. We were impressed to see 34% activity, and those black bars at the bottom we haven't begun to touch yet. And we know how to make substantial reductions to those numbers.
So I'd like to add one note on this one. Our focus is in the left slide where you see the observe, orient, decide. That was our pure focus for all of these activities. It was a little bit uncomfortable going into leadership to brief these numbers. It's hard to say that you're reducing something by 99%. But that's what it was. And when we look at the overall activity, the numbers are still significant. A 34% reduction was huge for the alignment activity, and it only went up from that point. And then I'll have you go ahead.
We accomplished this by using Scope AR's WorkLink application and a Microsoft HoloLens. In the past, development was purely a coding effort, and the WorkLink application gives us a purely visual interface to build these scenarios in. And I should mention here, developing the shop aid as 30% of my time, the 99% reduction in time that we saw took me 28 minutes to build, and it takes 4 minutes to duplicate for each of the remaining 5 panels.
Okay. So also on this, in the past, we would have developers who would spend months developing these types of applications. With Scope AR's WorkLink platform, we're bringing those numbers down, like Amanda said, to 28 minutes for a panel, 4 minutes for each additional panel. And the ramp-up time on the platform has also been reduced significantly. We can bring in a new developer and have them go through a half a day of training online, and then they can start building work instructions. That's what makes it different today from what we were doing back in the past, and what helps us get that overall return on investment. We can definitely save time on the factory floor, but the question is also how much time and effort it takes to build these products. So we're very happy with what we're seeing there.
So I'm going to talk a little bit more about the benefits of utilizing this technology within a manufacturing environment. I'm going to kind of skip to the chase. The biggest ones on here is expediting delivery times and lowering project costs. But the one that interests me the most is enhancing the user's experience. Shelley and Amanda did an amazing job on setting this up, and we've shown our AR work instructions to people from all the way from vice presidents of the company down to technicians on the floor to quality engineers. We've shown this to about 100 people, and we have not had one naysayer out of the whole group. Everyone seemed super excited about it and are thrilled to see where we go in the future with it.
We actually had a comment from quality not too long ago saying, you would actually have to try to make an error with these work instructions. So that's a quality buy-off right there.
We expected them to be our greatest naysayers, so we were shocked again when they made that comment, and very pleased. Another thing that we see is in the quantification, there's areas that are difficult to quantify. This last one, enhancing users' experience, it's hard to put a number on that. But with the numbers that we saw before, where the overall activity is being reduced by 50%, we saw activities where a 6-week activity was reduced down to 2 weeks. So that's over a 60% reduction in the overall activity time. There's spaces in there that we are unable to quantify, and we're trying to figure out better methods to quantify the overall, to see what's feeding into that to create that additional savings. And this is always our goal. You know, the story is that you can only accomplish 2 of the 3, that if it's faster and better, it must come at a cost, or if it's better and cheaper, it comes at a cost in time. What we're really excited about with augmented reality shop aids in the manufacturing environment is we can accomplish all 3. We've shown that we can build content more quickly, at higher quality, which is better, and at a lower cost, accomplishing all 3. If you're new to this type of technology, and if you're looking into getting into augmented reality products, I would definitely encourage to focus on which of these you want to put the most focus on. And for us, it changes from environment to environment or project to project. There are some projects where we're very focused on mitigating errors and increasing quality. There's other areas where we're very focused on time. And then, of course, we're always looking at cost. There's some times where we're less or more interested in that one compared to the other 2. I believe that's our last slide. So if there are any questions, we'd be happy to take a couple.
Any questions?
All right.
Come on, gang. There must be some questions. It's great to
That
actually
makes it easy.
see, once again, some real benefits and ROI. So there's got to be some questions. Can you put them on Slido, guys?
That looks like
Does
there's
that work? we haven't.
So for the work link, is there any animations in the 3D work instructions or the AR work instructions, or is it just simple?
Yes.
Could you just, Shelley, could you just repeat the question so that
So
recording.
the question is, in the work link, the Scope AR work link shop aids, were there any animations? The example that we showed here was a torque pattern, and it's more static. We can create that in steps so that they're verifying steps as they go, but there's other steps with alignment. One of the columns that you saw was alignment, and there are times where you have to move a component into place following a specific path. It's very important that you follow that path in placing the components. We animate there. We can animate to emphasize panels. We can add in highlight spheres to draw attention. There's keep out zones. There's a panel where we can have text work instruction. You can give a voice command. All you have to do is say show work link and it pops up wherever you need to look, which is also very popular with our technicians. Instead of having to go back over to an environment to look at specific text instructions, it's readily available. There's a number of things that the technicians have seen.
Yeah, I mean, we also animated things on the shop floor. We have 2 air manifolds that when you turn the manifold on, it actually has a lever that's about foot height, and we animated those as a trip hazard. So you have, even just in our environment where we're not even talking about the assembly itself, we're identifying potential hazards.
What if every single satellite was unique? Would it still be worth it? Yes. We're seeing return on investment on a single activity. And one of the things that we're doing, we still have the traditional work instructions there. And we do that I did that intentionally to mitigate concerns with converting. There's a huge risk in converting existing instructions over. But we've found that we can infuse the augmented reality instructions on top of what is already there and still save money and still have a positive ROI. As an example, we have programs where if an error is made, it's going to take at least a day to resolve because it goes through many layers of verifications and checks to make sure that the solution is correct. 1 day of delay costs over $1 million on that program. So you can see that the savings add up quickly.
Just one more, please, Shelley. One more.
Okay, let's see. I would like to talk to overall investment. I'm going to have to get some approvals in place before I talk to overall investment.
In terms of the operator feedback, absolutely. I didn't take the drawing and the MWI and go hide in a closet for some time. Decker and I worked very closely together, sometimes checking in several times a day. I would check in and say, I built this new step, let me know what you think. Let me know if it works, I'll come back tomorrow. And we did a lot of back and forth like that. Because we find that in the middle of the build, sometimes things just don't make sense. And we have to change the animation to match that. And that can take just a few minutes to update it, push it to the devices, and it's updated and ready to go.
Perfect. Thank you very much, guys.
Thank
That was
you.
really insightful. Thank you.